Hi, everyone, and welcome to the Anti-Doping Podcast, brought to you by the Partnership for Clean Competition. I'm your host, Dr. Marie McNeely, and today we are joined by our guest, Dr. Michaël Polet. Listeners, Mial is a faculty member in the Department of Diagnostic Sciences and head of the IRMS, or Isotope Ratio Mass Spectrometry, department in the Doping Control Laboratory, or DoCoLab, at Ghent University in Belgium. For more information on the DoCoLab, listeners, be sure to check out our episode 110 with Dr. Peter Vanino. And in today's episode, we are going to talk more about Michaël's career, some of his previous PCC Funded Research projects, as well as recent work developing novel methods for anti-doping sample analysis. So, Michaël, welcome to the show today. How are you?
I'm very well. Thank you for having me.
Well, thank you so much for joining us. We're excited to learn more about you and the work that you do in our conversation today. So perhaps to get started, can you share with us, how did you originally get interested in anti-doping science and find your way to your position there at Ghent University?
Well, after I obtained my master's degree in chemistry, I performed research at the Vice Analytical Research Center. And by performing this research, I got triggered by methodologies based on chromatography and mass spectrometry. And so about 1 year later, so that must have been in 2011, I started my PhD at the Doping Control Laboratory at Ghent University. And the doping, it's a particularly challenging field due to its dynamic nature and the need for state-of-the-art methodologies. It requires exploiting little instruments such as liquid and gas chromatography mass spectrometers to their full potential, and exploring and pushing the capabilities of this instrument is fascinating and allows providing answers to difficult anti-doping control related issues. And developing these innovative approaches, it's very rewarding and provides day-to-day challenges, and I'm glad I can do it on a daily basis.
Certainly. So then what brought you there to Ghent University specifically?
Well, that's actually where I did my studies. So it was like the next logical step to work in the lab there, and then from there start a PhD.
Very good. So then can you tell us, what are your responsibilities in your current roles? We mentioned you have a few different positions there.
Well, I guess a typical day, it involves tackling a wide range of responsibilities and tasks. I guess these can roughly be divided into 3 parts. So firstly, I'm head of the RMS department, meaning I'm responsible for everything that involves RMS. This first part consists of following up on routine GCRMS doping control samples, reporting and keeping the methods up to date and in compliance with the WADA regulations. Then the second part is research. So experiments are performed in the lab and various research projects need to be guided, papers written, oral presentations prepared, and also at regular times, new projects are written, instrument troubleshooting, and laboratory meetings are also part of life in our lab. And then thirdly, I'm also involved in teaching some practical courses at the university.
Excellent. Well, I know you've been doing great work there at Ghent University, and I'm curious to hear about how the Partnership for Clean Competition enters your story. So can you tell us, how did you first find out about the PCC and learn about the PCC's research grants?
Now, that must have been by talking to other anti-doping scientists from other doping control laboratories. I've been working with PCC for quite a while now. Most likely I heard about PCC at one of these anti-doping conferences.
Fantastic. And before we get into some of the details of your work developing new anti-doping analysis methods, perhaps we can first set the stage for listeners by giving everyone some background about gas chromatography versus liquid chromatography, since this is an important component of the work that we'll talk about today.
Yeah, so liquid chromatography is, of course, based on liquid. Chromatography uses liquid as a mobile phase. So your compound comes on a column, and the mobile phase is your liquid, which pushes your compound through your column. So that's liquid chromatography. And actually with gas chromatography, it's very, very similar. But then instead of liquid, you use gas to push your compound through your column. So mostly you will use liquid chromatography for more polar compounds because they're more compatible with solvent, of course. And for the more apolar compounds in general, you will use more GCMS. It's a rough division, but that's roughly how it goes, I would say. Both techniques, of course, they are compatible. So some compounds, they work better on LC. Other compounds, they work better on GC. So the complementary approaches, we will always need both techniques, I think. There are labs that try to focus more on LC, less on GC. Other labs, that's the other way around. But in the end, both techniques, they will remain very valuable. And both techniques together, they help us to cover all the doping substances that are currently on the WADA list. And there's been progress on both techniques and valuable research.
Wonderful. And I know, Michaël, you received funding in 2015 and also in 2018 through PCC research grants for some different projects focused on developing methods for comprehensive detection of doping agents. So can you briefly describe these two projects and maybe comment on the impacts of each of the projects in terms of further research that came after or adoption of these methods in routine lab work? And perhaps we can start with your 2015 project.
The main aim of the 2015 project was to drastically increase the sensitivity of the GC triple quad screening method by using chemical ionization, or CI, instead of the electron impact, or EI. In those days, it was a common practice to use EI. It was the standard technique used in those days for GC single quad. And when labs switched to GC triple quad, they continue using this EI. Now, in combination with triple quad, however, CI is a much better option than EI because it leads to a much more abundant molecular ion. So we realized this in our laboratory and started to perform research on this CI approach. And in the end, we were able to develop a new screening method using chemical ionization that had a much higher sensitivity for a wide range of compounds. And obviously, a higher sensitivity means that we can detect dopant substances for a much longer period of time. And then actually the project in 2018, and that one focused on GC-QTOF. So this led to the development of the first GCMS initial testing procedure using an open high-resolution acquisition. This allows to incorporate a lot more prohibited substances in a single method. And in addition, retrospective data analysis can be used to reevaluate previously acquired data. So one can, for example, many years later, search for prohibited substances that were unknown at the initial moment of analysis. And this provides a powerful tool in the fight against doping, and it deters athletes from doping abuse. And then at a later stage, we did research for several years on sulfated steroid metabolites. It was already known at that stage that sulfated steroid metabolites are in some cases present for a longer period of time than the traditional metabolites, prolonging the detection time of steroid abuse. However, the real potential of these long-term sulfated metabolites can only be exploited if doping control laboratories can include them in their initial testing procedure. Only then advantage can be taken of their extended detection windows. And in this project, new sulfated steroid metabolites were determined, so for several steroids. And even more importantly, strategies were defined that allow incorporating sulfated steroid metabolites in the initial testing procedure of doping control laboratories. And due to this project, the sulfated metabolites are now included in our initial testing procedure. And we already have some cases where we were able to detect steroid abuse due to these sulfated metabolites, where these additional metabolites were not detected. So if you would not have included these sulfated metabolites in our initial testing procedure, these doping offenses would not have been detected.
Well, I think that is remarkable. And I think these are really exciting research projects with important real-world applications in anti-doping. And for our non-chemists in the audience today, can you maybe explain briefly what this GC-QTOF or GC-QTOF procedure is?
Yeah, so it's actually a high-resolution approach. In the past, we used triple quads, where it's more a targeted approach, but with the GC-QTOF, it's a high-resolution approach, and so you have an open screening, meaning that you can incorporate a lot more substances. So it's one of the more, or at that stage was one of the more newer techniques that became available or accessible for doping control laboratories.
Excellent. And Mial, I know more recently you've been working on high temperature liquid chromatography isotope ratio mass spectrometry methods to use in testing for anabolic steroids. So can you first talk us through the limitations in some of the previous methods that led to the development of these high temperature methods?
Yeah, so doping control laboratories, they use gas chromatography combustion isotope ratio mass spectrometry, or GC-IRMS, to confirm the exogenous origin of endogenous anabolic steroids. And nowadays, laboratories, they analyze all urinary athletes' samples with a fast initial testing procedure. And this allows the isolation of suspicious samples. And then afterwards, the suspicious samples are analyzed with GC-IRMS as a confirmation technique. Isolation of suspicious samples occurs through the steroid module of the athlete biological passport, or the ABP. However, there are cases where the ABP will not label a urine sample as suspicious, even though doping commence with endogenous anabolic steroids was committed, and these samples will not be forwarded to GC-IRMS, and as such, the doping offense can go undetected, even though the GC-IRMS analysis on itself would be able to detect the doping offense. So the idea was to try to develop a high-throughput RMS method In that case, samples that enter the laboratory would be directly analyzed with IRMS. There would not be a need to filter out suspicious samples. Now with GC-IRMS, however, it is virtually impossible to develop a real high-throughput approach due to inherent characteristics of the technique. With LC-IRMS, however, that is a different story because you could, from a theoretical point of view, couple the LC cleanup step with the actual LC-IRMS analysis. However, developing such a LC-IRMS method for steroids, it is very challenging and requires tackling many technical barriers and solve many analytical issues. It is something which has never been done before, not only in our field, but also not in other analytical fields. And there are good reasons for that. So the first part of this project consisted in developing such an LC-IRMS method for steroids. So this year we succeeded in that. And then the following step is now coupling this LC-IRMS method online with the LC cleanup method, and that would allow for a high throughput approach, and that is what we are currently working on. But also here, it is very challenging and requires tackling many technical barriers and solving many analytical issues.
Certainly. And just to give our listeners a sense of what we're talking about when we say quote unquote high temperature, what temperatures are you looking at?
So we work with a maximum temperature of 200 degrees Celsius. So everything which is between 50 and let's say 200 degrees Celsius, that's what we call high temperature, temperature LC.
That makes sense. So then can you walk us through the general steps that are involved in the sample preparation and then running a sample through the high temperature liquid chromatography isotope ratio mass spectrometry method?
Well, the sample preparation steps, they are very similar to what we currently have for the GC-IRMS approach. So first we have a solid phase extraction, followed by hydrolysis of the steroids and a liquid-liquid extraction. Following, we have the dervatization step by acetylation. And then the last sample preparation step is the liquid chromatography fraction collection step. This is the most important cleanup step for obtaining pure compounds. So for our LC fraction collection, we do not use a conventional system where you would run your samples over one single column, but we use a two-dimensional LC cleanup setup, meaning that the urine samples are purified by running them over multiple columns instead, and this results in very pure fractions. This 2D LC cleanup method we already developed actually a couple of years ago. So in the past, to clean up urine samples, you would have one or multiple one-dimensional cleanup rounds where you would run your urine sample over one column, collect the fractions, dry them, and then rerun them over a second column. That is obviously very time-consuming, and with this method, we combined these multiple offline methods or runs into one single method where the sample is purified by running them over multiple columns at once. The last step is then combining the purified fraction into one and then inject this one sample on the high temperature LC-IRMS. Now, in order to develop a high throughput IRMS approach, we are now trying to combine this 2D LC cleanup method with the LC-IRMS method into one single analytical run. And this would allow for a high throughput approach. In such a setup, you could have a very similar sample preparation flow as you, for example, have for our current high throughput initial testing procedure for GCMS. So sample preparation on day one, and then overnight and the following day, you would have the actual analysis on the instrument.
So Michaël, for listeners who've never worked with these instruments before, can you first describe what these columns are and what they look like?
Yeah, so these columns, it depends. They can be, let's say, from 50 to 250 millimeters long. And in diameter, it's about, I would say, 1 centimeter. So they're like a stainless steel tube. That's what it looks like from the outside.
Perfect. Thank you. And as you're explaining the steps, it all makes sense and sounds very logical and almost easy to just walk through these steps one by one by one. But the high temperature methods that you used in this approach actually introduced some technological or logistical issues that had to be solved in order to move forward. You had to develop these techniques and methods and test them out and do some trial and error. And your team published a paper this past summer that was looking at multiple analytical columns and trying to see what works best under these high temperature conditions for steroid analyses specifically. So Michaël, can you tell us a little bit more about these challenges that you faced with the columns in your early experiments and how you kind of worked through them?
These ovens that we use for high temperature LC, they can heat up to a temperature of 200 degrees Celsius. So that's the maximum temperature that we can apply. And a first issue is that depending on the column, in many cases, this temperature is not high enough to elute our steroids. So steroids, they are very apolar, meaning that they stick very hard to the column so that they need high amounts of organic phase. Or in our case, with pure water, a very high temperature to get the compounds of the column. And for many columns, this temperature is simply not high enough. The biggest issue, however, is the stability of the column. So under normal routine laboratory practice conditions, an LC column needs to be replaced from time to time. So after running amount of samples on a column, the quality of the column deteriorates, and after a certain amount of injections, it needs to be replaced. It depends on the application, of course, but generally this is a couple of hundreds or thousands of injections. Now that is under ambient temperature conditions. Now you can imagine when you start using heated water on these columns, when you heat up your columns above 100 degrees Celsius, those are actually very, very aggressive conditions. It's basically pressurized steam you're pushing over these columns, and the higher you go in temperature, the worse it will get. So it basically destroys your column, and in most cases, it goes very, very fast.
So let's talk a little bit more about this paper. How did you go about choosing which columns you would ultimately use in this study to compare for this recently published study, and what were the ultimate findings?
I would say that about 90% of all columns that are used in liquid chromatography, they are silica-based. So these are very good columns. They are the workhorses for LC separations. Unfortunately, in combination with heated water, they're not an option. The silica basically dissolves. So we definitely need a column on a non-silica basis. And we tested various columns, such as, for example, porous graphitic carbon and zirconium and titanium oxide particles coated with various test near phases. Some of these columns, they were specifically designed for high temperature LC. But unfortunately, when they were tested under real life routine laboratory practice conditions, their performance was disappointing. Now, eventually, of all the columns that we tested, we did find one column that is suitable for high-temperature LC analysis of anabolic steroids. And if this column did not exist, it would not be possible to perform high-temperature LC separations of anabolic steroids. And if it would not be possible to perform a high-temperature LC separation, then it would not be possible to develop a LC-IRMS method. So we are very fortunate that this column exists. And the limits claimed by the manufacturer is a maximum temperature of 100 degrees Celsius. But our data shows that also at higher temperatures, the column is still useful. So we also encountered other columns where it was the other way around. So where manufacturers claimed a thermal stability up to 200 degrees Celsius. But when we tested them in practice, at least for our application, their thermal stability was very lower.
And then in terms of the findings then, so you kind of determined some columns perhaps worked better than others. What did you do with these findings, or what was that next step?
So once we found a suitable high-temperature LC column, we started developing this LC-IRMS method. That method focused on 4 steroids, so that is testosterone, its 2 main metabolites, 5-alpha-diol and 5-beta-diol, and pregantriol as endogenous reference compound. Now, unfortunately, in contrast to GC-IRMS, the 5-alpha and 5-beta-diol, they elute together at the same retention time, so we need to determine their carbon-isotope ratio together. We cannot determine the carbon-isotope ratio of the 5-alpha and the 5-beta-diol separately, so that is a disadvantage of LC-IRMS in comparison with GC-IRMS. Now, if you go through the publication, you will see that on many levels, LC-IRMS is able to reach the Waller criteria that are at this stage defined for GC-IRMS. Now, what is important here is that GC-IRMS, it has evolved a lot during the last 10 to 20 years. So new technical developments, you build up a lot of experience. We've been able to develop more performant methods. And with these developments, also the technical documents and the requirements where local laboratories need to comply with for their GC-IRMS methods. They have evolved a lot together with technique and with more strict demands over the years. So this is how it needs to be to ensure the highest standards of quality of data. Now, that being said, LC-IRMS, it's a brand new technique. It has never been done before, and it's unrealistic to expect that out of nowhere the technique will be able to do what GC-IRMS is able to do at this stage. So also this technique, it needs to be given the chance to evolve, mature, just as was the case with GC-IRMS. But again, that being said, on many levels, LC-IRMS is already able to reach the Waller criteria that are defined for GC-IRMS. And on some levels, GC-IRMS will always remain the better technique. On other levels, however, LC-IRMS will have the upper hand.
That makes sense. And I think this second paper that you referenced where you described the development and validation of these methods was really exciting to see. So can you share how well were these steroids detected? And can you perhaps explain a situation where someone would choose the high temperature LC method versus the GC method? Like how would someone in an anti-doping lab choose which method is most appropriate for their sample?
So at this stage, the GC-IRMS method is for sure still better than the LC-IRMS method. The real strength or power of this LC-IRMS method will come as soon as we will be able to couple it online with the 2DLC cleanup, because at that stage, you can have a high throughput approach, something that you cannot do with a GC-IRMS. So it's on that level that LC-IRMS could have a significant advantage over GC-IRMS.
Very interesting. And we mentioned specifically that you were looking at steroids. So do you see this method being valuable for other kinds of substances as well?
Yeah, for sure. There are other compounds where LC-IRMS can be used. In fact, it's more logic to use LC-IRMS for more polar compounds. So steroids, they're very apolar, so they fit better with GC-IRMS. But for more polar compounds, LC-IRMS is for sure a better option. One of these compounds can, for example, be Cara, for which there's also a GC-IRMS method. But like for this compound, it would make more sense to try to develop a LC-IRMS method.
Certainly. And I know we focused in on some of the issues surrounding the column selection or figuring out what the methods would be related to these issues with the columns. Were there other challenges that you had to work through in developing this method?
Well, other challenges were, of course, the LC-IRMS interface. It's different. So in the first weeks, months, half year, you do need to get to know the instrument and know the difficulties or the small hiccups that can happen with such an instrument. But that's actually the same as was in the beginning with GC-IRMS. There are just some small tricks you need to know on how to handle the instrument to have the best performance. So that's always a bit the initial phase of if you're testing a new technique. The first half year, it's getting to know the instrument and figuring out which are the small things you need to take care of.
Definitely. And could you perhaps comment on what you see as the potential impacts of this research that you've been doing?
In this case of this method, so anabolic androgenic steroids, they remain by far the most abused class of doping substances, much of it by the administration of synthetic copies of endogenous steroids such as testosterone. However, there are still endogenous anabolic steroid doping cases that are not picked up by our current detection protocols, and by taking our protocols to the next level is the way forward to reduce these cases to the minimum. So eventually, we aim at developing a high-throughput IRMS method, and developing this high-temperature LC-IRMS method was a first step we need to take to develop such a high-throughput approach. And with this high-throughput IRMS screening, we would be able to pick up a large part of those cases that still slip through the current detection protocols. Secondly, a high-throughput IRMS method is also highly desirable in those cases where there are a large number of samples that need to be tested on IRMS in a relatively short period of time, such as, for example, pre-season or regular season testing, and of course at the Olympic Games.
Certainly. And to help listeners put it into context, when you say high throughput screening, could you give us a sense of volume and time? So how many samples could be processed in what amount of time?
Then, of course, that will depend on the eventual high throughput method that we will develop. So at this stage, it's difficult to estimate, but I think around 20, 30 samples in the initial stage, that's something that we should try to aim for. And one day, so.
And then on a personal note for you, Michaël, what has it been like being able to work on this research that you can see could really impact clean sport?
I just like developing new methods and trying new approaches to existing techniques. And it's, at least for me personally, it's something very rewarding if you work for many months on something and then you see it actually works. So yeah, especially like the instruments, I like to push them to new boundaries or really search what is possible with certain instruments, combine certain techniques, and sometimes try to do things which hadn't been done before. So for me, that's something very rewarding.
I love it. And I know solving some of these big problems in anti-doping requires collaboration. So can you share, how do you collaborate with other stakeholders, whether it's funding organizations like the PCC, other laboratories, other scientists, or other stakeholders in the anti-doping or clean sport movement?
As a well-accredited doping control laboratory, we focus at countering the newest doping trends. So by constantly updating our existing methods and developing new, reliable methods. So research has always been a major focus, and these projects are a continuation of this policy. And for these projects, we try to, as much as possible, to collaborate with organizations such as PCC and WADA to join our efforts to move the anti-doping field forward. So PCC, it's an organization that primarily focuses on funding much needed anti-doping research, and they guarantee high quality review of the submitted research projects, and their reviewers provide constructive feedback leading to significant improvements of the project. These experts, they have various scientific backgrounds, not necessarily directly related to doping, allowing alternative views which can open new windows and provide new ideas. And then, of course, always in the final phase of our research projects, we try to inform other doping control laboratories and the anti-doping community in general of our findings as much as possible. So we do this by publishing our work in international journals and by presenting our data on various doping control related conferences.
And Michaël, have you ever attended a PCC conference? And if so, could you comment on it?
I was there last year at the PC conference. They're a very nice conference because you have really different stakeholders together there. So people from the lab, but also from USADA. And it's nice to see how all these different stakeholders mingle with each other and talk about various subjects. Also to see the other side. So I primarily have the side from the doping labs, of course, but it's also always nice to exchange ideas with, for example, people from PCC or USADA, what issues are that they're facing and come to solutions to certain problems altogether.
I love it. Well, I know there are still a lot of problems that remain in anti-doping that scientists and others are working hard to solve, but oftentimes there are limitations, whether it's funding, staff, technology, feasibility, or just hours in a day. So, Michaël, if you had all of the resources imaginable, what is one problem in anti-doping that you would most want to solve?
I will maybe try to answer a question from the point of view of a scientist trying to make more performant methods from my point of view. So nowadays we have very good methods capable of detecting a very wide range of doping substances. And the situation is very different now than, for example, in the 90s where we did not have, for example, a method for EPO where it was clear that was being abused at that time on a large scale. So that was problematic at that time. Now I think it would make more sense to allocate the resources to various smaller issues or projects that allows closing the gates for those rare cases or methods are still lacking under circumstances. And just to give you a small example, so indeed, the ICAR doping control laboratories, they have a method for ICAR, but the method is not ideal. It's very laborious, very time consuming, a lot of resource consuming. And I do believe there is room for improvement here. If we can make the method faster, less time consuming, less laborious, then we can also make it considerably cheaper. And this in turn would allow testing athletes for ICAR on a wider scale.
Oh, very interesting. I know there's a push towards sort of automation, making things faster, making things less hands-on. Are there things in the methods for anti-doping that you think are not going to ultimately be able to be automated? Are there things that just kind of need that human touch? What are your thoughts? For
example, the approach for EPO, that I think it's an approach that will always quite a lot of manual labor. It's just an inherent characteristic of that approach. So a lot of things we can automate, other things will require more manual labor. That's a fact, yeah.
Well, Michaël, is there anything else that you would like to share about your research or the work that you're doing right now at the DoCoLab?
Yeah, I'm always involved in different research projects. We are working on some interesting things now, but yeah, we will see. I can't disclose too much on everything, of course, but I hope for some interesting stuff coming up for following months or years.
Fantastic. Well, listeners, we'll have to keep an eye on work coming out of the DoCoLab. Michaël, if listeners want to learn more or they want to keep an eye on what's new coming from the lab, what is the best way for them to do so?
Easiest way, I guess, would be to go to our Ghent University website so there you can find an overview of the work that was and is performed at our laboratory.
Excellent. Well, listeners, definitely check out that website. Take some time to learn more about the amazing work that they're doing. And Michaël, it's been such a pleasure to have you on the show today. Thank you so much for your time.
Thank you very much for having me.
And listeners, it was great to have you here with us as well. If you haven't already, it would mean a lot to everybody here at the PCC if you could take a moment to rate our podcast and leave a review on your favorite podcast platform. And listeners, please note that the Anti-Doping Podcast features a wide variety of clean sport experts, and episodes may include statements and or viewpoints that do not necessarily reflect the views or values of the PCC. Thank you, and we look forward to seeing you on the next episode of the Anti-Doping Podcast.